Okay, so in the last class we started looking at design aspects of process control. What we said is there are 5 questions we need to answer, isn't it? The first question is what are the operational objectives that control system is called upon to achieve, isn't it? So this we have discussed several times that process control is typically called upon to achieve 3 things. Minimize the effect of disturbances on the control variable, that is nothing but suppressing the impact of the disturbance variable on the process variable. That is the first requirement. Second requirement is to make inherently unstable process stable, and the last one is to optimize the process. Okay. These are the 3 main requirements for which typically the process control is called upon. Okay. Then we said that we take the example of stir tank. In the stir tank, we are interested in maintaining the height of the liquid and we are interested in maintaining the temperature of the liquid mixture which is present inside the tank. So which is nothing but suppressing the effect of external disturbance, isn't it? In case of stir tank reactor, we are interested in making the operation stable, isn't it? So there are multiple operating points and typically we are interested in operating the reactor at unstable operating point. So in such cases we can apply the control as an external intervention to make the inherently unstable process stable. And the last one is in a distillation column, typically we are interested in maintaining the quality of distillate at bottom when there is a change in the inlet feed concentration, isn't it? So in such case, in this particular case also we are looking at suppressing the effect of external disturbances on the control variable. Okay. Typically the reflux ratio is the manipulated variable. The second question is what are the different variables which we need to continuously monitor in order to see whether the system is working fine or not, isn't it? Correct. So that is the second question. So in case of certain heater, we will be measuring temperature and height of the liquid, isn't it?
Sir, microphone turned off.
We can measure that by using thermocouple.
Sir, microphone turned off.
What happened?
The microphone.
Microphone is on.
Suddenly the voice, loudness.
The second question is what are the different variables which we need to continuously monitor in order to assess the process, isn't it? So in this case, in case of certain heater, we will be monitoring temperature and the volume. Isn't it that we can do directly by using thermocouple and differential pressure swing? Isn't it? Correct. The third question is, what are the different variables which we can manipulate ourselves? Isn't it? So in case of stir tank heater, the variable which we can manipulate is the steam flow rate or a coolant flow rate, isn't it? And the outlet flow rate of the tank, isn't it? These are the variables which we can manipulate. In case of distillation column, we can manipulate the reflux ratio, isn't it? Then the last question is, what are the different control configurations, and out of multiple choices available, which choice is the best, isn't it? So there are different control configurations, like whether you wanted to use a feedback system, feed forward system, differential system, which one, isn't it? Also sometimes you have multiple variables to manipulate. For instance, in a stir tank heater case, you can manipulate the inlet flow rate as well as outlet flow rate in order to maintain the height of the liquid in the tank. So you have multiple choices. Out of these multiple choices, which choice is the best? That is the question number 4. Isn't it? And once you have answered all these 4 questions, the last question is, how the manipulated variable will be changed in order to maintain the control variable to the desired state value. Isn't it? So this particular question is very, very important, primarily because so far we have identified which manipulated variable is there, which control variable is there, but if there is a change in the control variable, whether the manipulated variable should be changed proportionally, or is there any other control law by which we have to change the manipulated variable in order to have the desired effect, isn't it? So that part we have to answer in the last question, isn't it? So in order to understand this last question a little bit in more detail, in the last class we started with this usual example of stir tank heater, isn't it? Where we are saying that Fi and Ti are the inlet flow rate and inlet temperature of the feed, isn't it? So these are the disturbance variables, isn't it, in the given system. Outlet is coming with the flow rate of F and temperature T. In this case, the reaction mixture is getting heated by a steam flowing through the jacket. So in a way, my manipulated variable is Q, and my control variables in this particular case are height and the temperature. Okay. Let's see, if I am interested only in maintaining the temperature, in that case what I need to do, let's say this Fi is same as F. So inlet flow rate is exactly same as the outlet flow rate. So in that particular case, the height is not going to vary. Is it? The only variable which is going to vary is the temperature. If there is a change in Ti, the only variable which is going to vary is this temperature. Is it? So in this particular case, what we are going to do is, we are going to measure the temperature. So temperature measurement is represented by T. Once we measure the temperature, measured value of temperature is compared with the set point, and that will give you the error. Based on the error, temperature controller is then going to manipulate the flow rate or the heat supply to the system. Is the system. Correct? Now, in this particular case, since we are saying that the height is not changing, that means inlet flow rate is exactly same as the outlet flow rate. Isn't it? The only control variable in this particular case is the temperature inside the reactor. I wanted to write down the balance equation. So what balance equations I am going to get in this case? This is the balance equation we are expected to get. V rho Cp dT by dt is given as Fi into Ti minus T plus Q by rho Cp. Why plus sign here? Because heat is supplied. If the heat is taken by the coolant, in that case it will become minus Q by rho Cp. And also there is no reaction occurring, and therefore reaction term is omitted, isn't it? Otherwise we will have one more reaction term coming in here based on how much heat is generated because of reaction, or how much heat is consumed in the endothermic reaction because of reaction. Correct? So since no reaction is occurring, only the reaction material is getting heated to a desired temperature, we have only two terms here. This term is nothing but inlet minus outlet, and this is nothing but the heat supplied by the steam. Correct? Now this particular equation is giving me the dynamic behavior. Dynamic behavior, isn't it? But if you look at the given system is at a temperature. If you look at the disturbance variable Ti is exactly at Tis for all the time, isn't it? So at time t equals to 0, we are adding a disturbance. That means this Ti is getting changed to another value from its steady state value, isn't it? So because of change in this Ti, how my output variable is going to change? If I look at this particular thing, you will see that my outlet temperature is going to increase and then it is going to settle to a fixed value, isn't it? So you can see that in this particular region there is a transient behavior is happening, dynamic behavior is happening, and after that you get a fixed output value. So that means what? You are reaching to another state. Correct? So in this case we have plotted T minus A. So we have directly plotted the error in this case. Remember, if I plot only T, in that case it will start from the initial value of Ts and it will reach to a new value. So if I plot T minus Ts, it is starting from 0 and then it will reach to 0. Correct? The output is clear to everyone why we are getting this, isn't it? If you look at this particular example here, if I change here, definitely the inside temperature is also increasing. That one we are representing. Isn't it? And it will not continuously increase, it will reach to a steady state value. So that is what we are seeing here. It is increasing and then reaching to a steady state value. Make sense to everyone? Now let's write this equation again at a steady state. So at steady state, this entire term will become 0 and the remaining two terms will become f rho Cp. This Ti will become a steady state value. So that becomes Tis. And also T will become a steady state value. So that becomes Ts. So Tis minus Ts plus the amount of heat supplied will become Qs. So this is the equation at steady state. If I subtract this particular equation which we have obtained at steady state from the original dynamic equation, what we get is we get the differential equation in a deviation form. We get the differential equation in a deviation form, and there is a reason why we obtained a differential equation in a deviation form. When you will look at the Laplace transform for such systems, you will see that Laplace transform of derivative if you are taking, and if you are having the differential equations represented in a deviation form, the initial value becomes 0. Okay, so that is the reason why we are taking the deviation variable here, because that will enable solving the system easily. Okay. So here this differential equation is representing as d rho Cp, d minus Ts. So this is nothing but what? d by dt. It is nothing but how the error is changing with respect to time. And right hand side, f rho Cp Ti minus Tis. So I can represent this as Ti dash, which is nothing but how much Ti is changing from its steady state value. Similarly, I can represent this as T minus Ts. I can represent as T dash. So that is nothing but how much the actual temperature inside the reactor changing from its steady state value. And similarly, the last term will also we can write down as Q dash, which is nothing but how much Q is changing from its steady state. Correct? So this is the equation which we have obtained. Now in this particular equation, T minus Ts is the error. T minus Ts is the error, isn't it? Ultimately, I am interested in maintaining the value of the temperature exactly at Ts. Isn't it? I want to maintain this T minus Ts 0. This is the error. Even if there is a disturbance occurring in the system, my final aim is to have this T minus Ts equal to 0. Isn't it? So you can see that in this particular equation, T minus Ts is the error, which I wanted to make it 0. Ti minus Tis, this is nothing but what? This is nothing but the disturbance variable on which you do not have any control. Isn't it? It's continuously coming in the system, you cannot change this part. The only variable which is there in your hand is Q minus Ts. So Q is the heat supplied. So by having more flow rate inside, more flow rate of the steam inside the reactor, you will have higher value of Q. So this particular variable is in your hand. So Q minus Qs is the actual manipulated variable which is there in your hand, isn't it? Now the question here is, if you wanted to control this system, is what? Suppressing the effect of disturbance on the system. When I am saying suppressing the effect of disturbance on the system, what it means? I am actually interested in having this T minus T as 0 all the time, even if there is a disturbance at time t equals to 0. That is what I am interested in. In this particular case, at time t equals to 0, there is a disturbance coming in the system, and because of that, this T minus Ts is increasing, isn't it? But actually, I am interested in maintaining T minus Ts 0 at all time, even though there is a disturbance coming in, isn't it? So now my aim is how I can change this Q minus Qs in order to get this T minus Qs 0. This is what I am interested in control. So when I am saying controlling this system is what? I wanted to change this Q minus Qs in such a way that this T minus Qs becomes 0. Right? Now if you ask this question to a layman, what he will say? He will say that okay, I am interested to change T minus Ts, I wanted to make it, and I know that T minus Ts is getting messed up, isn't it? Because of change in Pi minus Tis. Let's change this Q minus Qs proportionately to T minus Ts in order to make it 0. Isn't that is what the layman will say? Isn't it? By whatever the extent my system is messed up, my external intervention should be proportional to that. That is what I am saying in layman's term. How much my system is messed up, around the same extent I wanted to change my manipulated variable in order to make my system stable. Correct? Make my error 0. So in this case, where I am taking this Q minus Qs proportional to error, then the control action and the controller which is based on this particular rule is called as proportional control. So when I am saying a proportional controller, what it means is the control action which I am going to perform by manipulating the manipulated variable, this change will be proportional to the error present in the system. Okay. So how much is the value of T minus Ts proportional to that? I am going to change T minus Ts. That is what is it. So simplest control law is nothing but this Q minus Qs, if I take it proportional to T minus Q. Now if you look at this system, if the temperature inside the tank is higher, in that case this Qi should decrease, and whenever the temperature inside the tank is lower, in that case I should increase the Q. Correct? So it is opposite. So that is why minus psi is coming. So Q minus Qs is actually equals to minus alpha T minus Ts, where this alpha is nothing but the proportionality constant. This alpha is nothing but the proportionality constant, which is also called as proportional gain, controller gain. More details on this gain we will look at once we will move ahead. Now, once we have decided that this Q minus Qs I am going to change proportionately with T minus Ts using this particular law, then I can replace this Q minus Qs by minus alpha T minus Ts. So if I put that in this particular equation, this is the equation we have to solve. This is the equation we have to solve. Okay. Now, if you look at this particular equation, as you increase the value of alpha, let's say if you put the alpha equals to 0, in that case what it means? You are not adding any control action at all. You are not changing T minus Ts, isn't it, at all? You are not adding any external intervention if you are putting alpha equals to 0. So in that case you get this curve, which is nothing but no control at all. No control at all. But when you have, let's say alpha equals to 1, in that case you get, see, your final value is settling to a slightly lower value than no control. So if you take this particular curve, this particular So at steady state error, how much is the difference between the desired value and the actual value? That is nothing but the offset. So you can see that you can get the zero offset. You can get the zero offset only by having this alpha tends to infinity. Only and only when your alpha tends to infinity, your error is going to become zero. So you can get the perfect control only and only if the controller gain alpha is infinite. Okay. Now there is a problem with using a very, so see, when we are saying a particular variable is infinite, what it means physically? Physically it means that you have to use a large value. Isn't it? Now there is a problem with using a large value for alpha. Why? Because this entire analysis depends on what error you are getting, what error you are measuring. Remember, the control, this particular control action you are going to perform by measuring the error. When I am saying measuring the error means what? I am going to measure this t. I am going to measure this t. Remember, here I am measuring this t by using a thermocouple. And when I am measuring a particular variable, it may not be accurate. Isn't it? There could be some problem with the measurement. There could be lag. There could be time lag. Isn't it? So what it means is, if you are measuring the temperature at time t equals to 0, actually that is not corresponding to time t equals to 0. In fact, that is corresponding to a time a while ago. Not exactly a time t. Because every instrument, you take the name of any instrument, every instrument has some date time associated with it, some lag time associated with it. It is not immediately. Okay. So what it means? It means that whatever the error you are measuring in this equation, this error is actually corresponding to a time a while ago, not exactly at that particular instant. So if you are using a very large value of alpha, you are actually using a very large value of alpha based on the error which itself is not correct. Isn't it? And that may lead to the instability of the control system. Isn't it? Because your measurement is flawed. Even though you use a very sophisticated experimental setup, still you will have some dead time associated with the error. You cannot use a very large value of alpha, primarily because your control action is based on a wrong measurement. You have to be conservative in using the value of alpha. So even though this entire analysis is predicting that I should have alpha as large as possible, but in a real life application, I should be using this alpha value conservatively. I should not be using a very large value of alpha, because very large value of alpha I can use only and only if everything is working perfectly. But real life system is not going to work perfectly. Your measurements are not going to be perfect.
Sir, how do we set the value of alpha?
So alpha value is okay. All these parameters, there is something called as controller tuning. We find out the best values of alpha. Okay. There are some controller tuning methods like Ziegler-Nichols controller tuning, Cohen-Kuhn controller tuning that we will see as we go ahead. But alpha is the user-defined parameter. You will have to specify.
Yes, no, I was asking like what is alpha signifying physically?
Alpha signify, okay. Alpha is nothing but what? Okay, so if there is a error, let's say 0.5, how this 0.5 is getting converted to actual manipulated variable, there is some multiplication factor is there.
Yes.
That multiplication factor is alpha. So it is nothing but a strength of the controller. Higher is this multiplication factor, more will be your output. Okay.
Right.
So here alpha has to be positive. The proportionality.
This constant is always positive, yes. This alpha is always positive.
So that's why the proportionality constant is negative.
So that you clearly get from the system itself. Let's say if the temperature is higher here, what you should be doing?
Sir, if temperature is higher, then
Then you will
we should
reduce
reduce
the
the Q, right?
When temperature is low, you will increase the Q. So it is opposite. That behavior you can capture only by having a negative sign. Okay.
Sir, but you said that if we are alpha is tending to infinity, t minus ts is going to 0.
Yes.
So even if there is a different error, still it should be going towards 0 only, right?
If there is a
So you said there's dead time,
Huh.
correct? So that particular error is of a time period which is few time periods back before.
Huh.
So now if we are
So you are
sending
assuming
alpha,
here that the error will be always positive. That is not true.
okay.
That is not true. Sometimes it is negative also.
Yes, correct.
Okay. So let's say if you have if you use the very large value of alpha, so what will happen? It will decrease the temperature.
Yeah, it will.
Again it will increase the temperature. So you will see that
A
you will
lot of
have a
fluctuation.
fluctuations. You will get a fluctuations, not a single curve. Okay.
Okay.
All right. Okay. So now we have what we have concluded here is proportional controller is the simplest control. Why? Because you are, there is nothing is required. You are applying the control action which is proportional to the error. Isn't it? Which is natural. Which is natural. But the problem with the proportional controller is not going to eliminate your steady state error completely. You will have the steady state error associated with it. Okay. Correct? So now the question here is, can we do better than this? Is there any way we can improve this? Is there any way we can improve this? Now I wanted to get rid of this offset, I wanted to get rid completely. Isn't it? So what should be done in order to eliminate the error? Changing the power of error. Which equation? This equation. Changing the power of equation square. Still the error will not be. Still the error will not be. It will decrease, but it will not eliminate. So there is something called as integral controller. Okay, that is what we are going to do. So there is something called as integral controller. What this integral controller is doing is the control action. You can see that Q minus Qs is proportional to the area under the curve. So as long as there is a error is there, it's going to continuously increase your control action. So you can see that this particular equation you will put it. If you have an integral sign here, and this alpha dash is nothing but the parameter with respect to the integral action, isn't it? You can see that if I put this particular term here in place of Q minus Qs, this equation can eliminate the steady state error completely. It can eliminate the steady state error completely. Okay. And this particular control action is called as integral control action. So we have seen proportional control action previously. Now this is the integral control action. Okay. Much more detailed, much more meaningful insights on this you will get to know once we do Laplace transform. Okay. Here I am only representing things more or less in a qualitative manner, but we are going to solve these equations completely by using Laplace transform as we go ahead, and then you will appreciate more why I am saying that this particular control action is going to eliminate your error completely. There will not be any steady state error. You will mathematically prove. You will prove mathematically both. For proportional controller, you will always have an offset, and in the integral control, you will never have an offset. But there is a problem with this particular control. So you can see that proportional controller, you get a steady state error like this. But when you have an integral control action, you can see that your offset is decreased, because as you give t tends to infinity, ultimately your response is going to settle to a zero value. That means what? A steady state error is zero. This word steady state is very important. When I am saying steady state error is zero, is what? I am looking at the error value at t tends to infinity. At a large time, what will be the error associated with the output? That I am going to look at. Isn't it? So here you can see that for a proportional controller, doesn't matter if I take a large time, still I will have a offset. Isn't it? But in the integral control, where I am having t tends to infinity, you can see that all these curves are settling to a zero value. Settling to a zero value. Okay. So steady state error is not there if you are using integral control action. Integral control action and integral control action. What integral control action is doing? It is actually performing the control action proportional to the error, proportional to the area under error curve. So this is nothing but what? Error, isn't it? So I am actually obtaining the area under the error curve. When I am integrating this error with respect to time, actually I am obtaining the area under the curve, isn't it? So you can see that this particular control action keep on increasing your control action as long as there is error, isn't it? Isn't it? So that is why this particular control action can eliminate the steady state error. It can eliminate the offset completely. But this particular control action has another drawback. This control action has another drawback. The another drawback here is the system is going to become complex. That is one thing. And the another drawback here is it is going to make your system unstable. It is going to make your system unstable. Why? Because you can see that it will perform the more control action. Because of that, it will decrease and it will go below zero line. Again, it will increase. So you can see that it is integral control action. There is the oscillator behavior. There is the oscillator behavior. And that you can clearly see here. Why? Because whenever you are performing the integral action, that is with respect to the measurement. So whatever error you have measured is not actually corresponding to the same time. So you will end up applying more control action at a given time than it is required. So you can see that with that it goes down a zero line. Then again perform the corrective action, more corrective action. So it again goes back. So you can see that you will get the oscillatory behavior. The oscillatory behavior is obtained using the integral control action primarily because of inaccuracies in the measurement. Inaccuracies in the measurement. Okay. Alright. So we started with the proportional control. We said that the corrective action should be proportional to the error. Then we said that it has some problem because it is not going to eliminate the offset. Then we said that okay, we will add the integral control. So integral control is going to eliminate the offset, but it will add the instability in the control system, isn't it? Now another question here is, can we do better than this? Is there any way I can eliminate these two problems? I can eliminate the offset as well as I can eliminate the instability. Can we do better? So we can use the differential control. Now the another question is, why differential control is going to help in stabilizing the process? Anyone? Differential control can help in stabilizing the process. Why? So when you are taking the derivative of something, let's say any curve is there, when you are differentiating that particular curve, so what you are actually finding out? You are finding the slope of that curve at a given point. So whenever you are finding the slope of a given curve at a given point, what it means is you are predicting how this curve is going to behave in future, isn't it? So when you are taking the derivative, it is nothing but anticipatory in nature. How the curve is going to behave in future, that is what you are trying to anticipate when you are taking the derivative, isn't it? So when you are using the derivative term additionally, if you are using the derivative term additionally, you will see that if you use the derivative term additionally, you will see that this derivative actually anticipates the error in the future, and based on that you can apply the corrective actions more correctly compared to proportional controller and integral control. So when you are adding the derivative action in the control system, then it becomes PI integral. P for proportional, I for integral, and D for derivative. Now the disadvantage of this particular controller is, derivative controller has a disadvantage in the sense that your control system is becoming now more complex. you have proportional, you have integral and derivative. Isn't it? There is a rule in a process control that the simplest control system which works well for your system should be used. You should not make your control system unnecessarily complicated. Why? Because if you are using a PID controller, you have 3 parameters to tune. When you use only a proportional controller, you have only alpha to tune. When you use PI, you have alpha and alpha dash. And when you are using PID, you have 3 parameters: alpha, alpha dash, and alpha double dash. 3 parameters you have to tune. Isn't it? So when you are using a PID controller, of course you get a very good control, but then you have 3 parameters to tune. Isn't it? It is more complex than proportional controller and PI controller. Another interesting thing to note down here is proportional controller can be used alone. You can use proportional action alone for controlling the system. You can use integral control action also as standalone for controlling the system. But you will not be able to use derivative action alone for controlling the system. You will never hear derivative control. You will hear only proportional derivative controller, proportional integral derivative controller, but you will never hear only the derivative controller. You can have proportional controller, you can have PI controller, you can have only I controller in a special case. But you cannot have only derivative controller standalone. Okay? Clear? Why? Can anybody tell me why?
Because when we are finding the slope, it will indirectly become more unstable, right?
So for instance, let's say you have a curve like this.
Tendency
Okay.
नहीं मतलब ऐसा कुछ
So let's say your error curve P minus
attendance
Yes, which is nothing but the error. This error curve, let's say this is the zero line, this is the zero line. Isn't it? Let's say your error curve is
ठीक है
something like
Last
this.
mark कर रहे
What will be the derivative action here?
downward
Downward. Isn't it? Even though you have the error present which is positive, but you are applying the negative intervention in this case. Isn't it? So you can see that the derivative control action cannot be used standalone. Okay. Integral control action you can use standalone, you can use proportional control action standalone, but not derivative. Alright. What is written here? You can see that if there is a state input at time equals 0, no controller will get this particular curve. This P controller, there is a slightly reduction in the offset. Then PI controller is there. PI controller is setting to a 0 value, but it has more oscillations. But when you are using the derivative control action, PID control action, you can see that even the oscillations are derivative. Even the oscillations. Now let's look at the, so far we have seen the individual cases, like we have seen stir tank heater, then we have seen the reactor, then we have seen the distillation column. But typically if you look at a complete plant, in the complete plant all these units are connected with each other. This is one example where the complete plant is looked at together. You can see that there is a reactor which is producing C, so A plus B gives C. So C is your desired product. A and B are the reactant. So you can see that A and B are added to the reactor. So Fa and Pa are nothing but the flow rate and the temperature of the reactant A coming in the system. Similarly, Fb and Tb are nothing but the flow rate and the temperature of the inlet feed stream B. Then the reaction is endothermic, so the steam is passed to the jacket, and by condensing the steam, the heat is added to the reactor, and because of that, this reaction is happening A plus B gives C. This entire reaction mixture is then pumped by using a pump to the distillation column. Isn't it? And in the distillation column, you can see that A and B are separated as a top product. Isn't it? And the C is separated as a bottom product. So you are removing the C as a bottom product. A and B separated at the top product. You can recycle that and send that to the reactor. Now, in this case, my control objectives are what? In this case, my control objectives are keep the flow rate of the desired product stream Sp at the specified level, keep the required purity of the C in the product stream. So what we are interested in maintaining this Fp to a desired value, and also we are interested in maintaining the purity of C. Okay. So these are fixed. So whenever these control objectives are fixed, what will be the economic objective in this case? Economic objective will be to maximize the profit, isn't it? So I wanted to run this entire process in such a way that the profit is maximum, isn't it? Correct. So that is what is written. Maximize the profit from the operation of this plant since the flow rate and the composition of the product stream are specified. So you can maximize the profit by minimizing the steam use. You can maximize the profit by recycling your unreacted reactant back to the reactor. Isn't it? Correct.
Yes.
Then operational constraints here are you don't want your CSTR to overflow, and you don't want your distillation column to flood or go dry. Isn't it? So these are the operational constraints, these are the operational objective and economic objective here is to maximize the profit. Now disturbances are what? Disturbances are flow rates, composition, temperature of the streams of the two raw materials, temperature inside the distillation column, the temperature of the coolant used. This can change. So you can see that this FA, TA, FB, TB and the steam temperature this can vary. Isn't it? So these are the disturbances coming in the system. And with these disturbances coming in the system, you have to make sure that this tank is not overflowing, this distillation column is not flooded, and at the same time you wanted to maximize the profit. Correct. Now this particular problem is very simple, but it is not simple. Particularly why? Because there is a recycle stream. So whenever the recycle stream is there, I don't know whether you have done the design course or not. Whenever there is a recycle stream, usually the interesting variable is the ratio of the concentration, not only the concentration. So in this case, the more important is FA by FD. So ratio of the concentrations are important in such cases because there is a recycle stream. How much is recycled back? Based on that, you have to manipulate, isn't it? So that is what is written. The system is complicated, FA by FB, and the temperature is required to be maintained inside the reactor. Different hardwares used are, you have to have the transducers to measure the pressure, there will be transmission lines, controller, etc. So this is the system, a typical system I am representing here. Okay? Is it clear? Alright. I think how many chapters you have completed so far in the driving book? If I am not wrong, 4 or 5 chapters you have completed.
5.
So please buy book. Please buy book and don't just look at the slides. There is a lot of material we are covering. Okay. So don't be in the wrong place that only 2 slides are done. I have already put the slides, 100 slides I have put. Okay. So almost I think we will cover around 300 slides in this course. More than 300 slides. 100 slides I have put. 100 slides. I have what? Please buy the book. There are 2 types of books.
100 pages हो गए बुक के पेपर लिख के बाद
One is the black color and the other one is the green color. There is no difference in both the books. You buy whichever is there. Okay. In fact, that green color book you can get slightly at a lower price compared to the black color. And if you don't want it to buy, all your seniors having this copy. Please get it. पैसे ले रहे हैं कैसे सीनियर है
Sir, sir, is this kind of I borrowed it from senior.
You borrowed it from?
My senior.
No, this will not work.
Okay.
Why? Because you can Xerox anything inside.
Okay.
That is the problem. I have no objection in allowing you this. But then there are some students which misuse this.
Okay.
Then I have to depute one TA to check each and every book. And I have done last time. I have asked one TA to check each and every page whether there is anything other than the book is Xerox. People have done. Over the period I have seen some other book is getting Xeroxed inside, some other material is getting Xeroxed inside, isn't it? Okay. Sometimes people even put that entire solution manual people have bought along with this. I don't know from where they got, isn't it? So that is why the rules in this course is nothing from the previous year question papers, nothing from the unsolved which is there in the backside of the book will appear. All the questions will be new. So that everybody is having a fair chance to score. There is no undue advantage to anyone. Okay? Alright.
चली
So
गई.
we will start with.
हमारी नहीं हुई. हमारी फर्स्ट रो की नहीं हुई थी.
Can we go ahead to the new topic?
ये क्यों ऊपर नहीं किया सब कुछ. पता नहीं दिख नहीं रहा. दिखेगा तो.
And that was the syllabus in your gate. Gate examination, that was syllabus is there. I am not doing anything more than whatever is mandated.
हाँ हम गेट की थे.
Okay. Alright, let's start with this topic and we will cover this again in detail in the next class. So in this case, what we are looking at is a modeling consideration of the control problem. So far we have discussed several things qualitatively. Now we are looking at things slightly more and more in a detailed manner. So every class you will see that some more details we are adding. Same example will be there, but some more details are added. So now this is the same example of continuous certain reactor. Continuous certain reactor. FI and PR are the inlet, FI and PR are the outlet. Height you wanted to maintain. You wanted to maintain the temperature inside the reactor. Increase the calculated variable. Again, for a simplicity, let us assume that this FI and this outlet flow rate both are same. So if inlet flow rate and the outlet flow rate is same, what will happen to the height? Remember, when we look at the height, A ds by dt is given as Fi minus F. If Fi is same as F, in that case height is not going to change. So the first differential equation which we have seen in the model, that is not required. Why? Because the inlet flow rate is exactly same as the outlet flow rate. Now let's look at the another equation. The another equation is how the temperature inside the reactor, inside this figure is going to change. So that will be given by V dt by dt, Fi Pi minus T plus Q by rho Cp. Isn't it? This is the equation which we have. Now let us assume that, just for a simplicity, let us assume that the steam supplied here is a saturated steam. Saturated steam. So this saturated steam is condensing inside this coil, and because of that the heat is liberated. So whatever the heat is coming out from this coil will be given by what? Latent heat of vaporization multiplied by the flow rate of the steam. Because we are assuming the saturated steam. Isn't it? So this Q will be given by lambda into Fst, where lambda is the latent heat of vaporization. So lambda into Fst is the amount of heat supplied by the steam condensing inside the coil. So I can replace this Q by lambda Fst. So this becomes V dt by dt Fi Pi minus T plus lambda Fst by rho Cp. If I rearrange this equation, what we get? dt by dt is given as this Fi by V if I take. So Fi by V, that becomes 1 by tau. And this tau is very similar to the space-time which we see in the reactor engineering. Isn't it? So Fi by V is 1 by tau, and this Ti will remain as it is, and there will be minus 1 by tau T plus lambda Fst divided by rho Cpv. So we can take that 1 by tau and this T on the left hand side, that becomes dt by dt, and 1 by tau we are representing by alpha. So that becomes alpha T here. And right hand side is 1 by tau Ti K Fst. So now we have rearranged the equation like this. We have rearranged the equation specifically like this. Why? Because you can see that the left hand side the only variable is T, which is the control variable, and right hand side you have two variables which are nothing but Ti and Fst, where Ti and Fst both are the input variables. This T is the output variable. So left hand side is written in terms of the output variables, whereas the right hand side is written in terms of the input. Out of these two variables, Ti is the disturbance, whereas FST is nothing but what? FST is the magnitude. Okay. Once I get this equation, then we have to solve this linear differential equation. Solution of linear differential equation can be isn't it? dy by dx plus py equals to q. That is the standard linear differential equation. Solution is integrating factor you have to multiply, isn't it? So y into e raised to the power integral p dy p dx, isn't it? Should be equals to integral of q into e raised to the power integral p dx plus c. That is the solution of linear differential equation. So the same formula you have to apply and solve the linear differential equation and see what type of equation. That means
इसे जांच के देखा है ये सारी मैंने
so please buy book, and if you don't want to buy it, and if you don't want to do that, then
ये खरीदी नहीं है मतलब सीनियर से ली अभी जाऊंगा खरीदने देखता हूँ
अभी यही बात हुई
मैं कमीशन तो था